Thank you. I'm Yizhi. I'm a postdoc in the Scalable Solvers group. In this talk, I'll put out a new perspective on solving linear algebra tasks with quantum computers. I'll focus on eigenvalue problems, which motivates the title of my talk. Quantum computers are promising for studying physical systems, where the number of system configurations can really grow exponentially with the system size. An exciting consequence is that the quantum algorithms may address real-world challenges that are intractable with classical computing. And elucidating molecular phenomenon is one such example. So the middle figure shows a nitrogen fixation process that converts hydrogen and nitrogen into ammonia. This reaction is catalyzed by a powerful but rather complex structure shown on the right. Although the reactants and products are very simple, understanding the mechanism requires knowing the stable configurations of the catalyst, and therefore solving a pretty complicated Schrodinger equation. Here, we're interested in finding a few eigenpairs of a metabolic Hamiltonian. This is an operator that encodes the energy levels of a molecule and where electron density is concentrated. And quantum computers provide a platform to simulate these kind of systems by leveraging the nature of quantum mechanics, for example, superposition and entanglement. And so our goal really is to design algorithms that are computationally appealing and at the same time practical for very noisy quantum devices. And here's an outline of the talk. First, we'll introduce real-time evolution as a building block for algorithms that solve many-body eigenvalue problems. And next, we will explore two leading real-time methods. These are the subspace and signal processing methods. Next, we dive into how randomized algorithms can combine these two methods. This gives the so-called signal subspace methods, and we'll show a few numerical benchmarks. Okay, so the main tool we're going to use in this talk is the real-time evolution of some wave function. To see the connection between time evolution and energy estimation, we can write out the time-evolved initial state in the eigenbasis of the Hamiltonian H. So the resulting expression on the upper left is nothing but the sum of sinusoids. More precisely, the energies and weights of the eigenstates are all reflected in the phases and the amplitudes of the sinusoidal signal, which can be processed classically once data containing the eigenmodes are sampled on a quantum computer. And why real-time evolution? So the short answer is the time evolution is quantumly native due to its unitarity and also BQP completeness, roughly meaning that it is quantumly easy in the language of computer scientists. So the middle two figures show some experiments that demonstrate the utility of running dynamics on different actual devices. For time evolution, also a zoo of algorithm has emerged in past few years, many actually achieving theoretically optimal scaling. So our task is to recover spectral properties from the underlying dynamics with minimal resource. By spectral properties, we actually usually mean that we want to recover the low-lying energies colored in red here. So next, I'm going to introduce two classes of real-time methods that form the backbone of our work. So these are the subspace methods and signal processing methods. So the subspace methods, they rely on the idea of projecting the exact Schrodinger equation onto some subspace of smaller size. So in exchange, we'll get a reduced problem that variationally approximates the original problem. But since the reduced problem is much smaller in size, we can solve it efficiently. In particular, a real-time subspace can be built by successively evolving some initial quantum state. And as we evolve the state, the individual eigenphases would wrap around the unit circle at different rates. So when we combine these time-evolved states, the high energy contribution can be suppressed by phase cancellation. Alternatively, signal processing methods, they rely on the idea of filtering out dominant eigenmodes through some spectral techniques. Specifically, Fourier techniques can be applied to resolve some target frequencies. If we look at the bottom, for example, we can use a window Fourier transform to isolate out the dominating eigenmodes. Here, f is a window function in the time domain, and f tilde is the Fourier transform. So if f and f tilde, they decay rapidly, then the locations of the spectral peaks in the frequency domain can be found pretty efficiently. So the subspace methods and signal processing methods, they all have their unique strengths. And for comparison, we can list some important features in this table. So the first column shows the sampling cost for getting a data point under time evolution, where epsilon 1 is the statistical error because we're sampling on a quantum computer. The two methods have the same cost because they're using the same circuit. The second column shows the total runtime, where epsilon is the energy error. Here, subspace methods often fall short of achieving the 1 over epsilon optimal scaling, and they're often susceptible to noise because the projected eigenvalue problem is often ill-conditioned. By contrast, many signal processing methods, they have optimal runtime. But on the other hand, the subspace method, they don't assume the presence of dominant eigenmodes, which means the initial state preparation can be simplified a lot. Moreover, solving an eigenvalue problem gives access to eigenstate information, which is missing in the Fourier techniques. Now we ask whether we can combine the strength of the two approaches to target the ground and excited states of a Hamiltonian. Our idea is that instead of processing a single signal, we can process a subspace of signals by sampling many expectation values at the same time, which we refer to as the observables. These are formed by applying some operators O to the left. Think of it as some excitations and time evolution operator to the right of some initial state. And by using randomized algorithms, we show that the sample complexity scales only logarithmically with the number of observables. Importantly, this complexity can be independent of the system size or the locality of these O's, giving us the freedom to introduce global perturbations to the wave function and really build a rich subspace. So we call this multi-observable method MODMD, where quantum randomized algorithms help us construct the observables, and DMD, which is the acronym for dynamic mode decomposition, is the classical post-processing strategy. So getting into a bit more detail, we can first look at the data generation step on a quantum processor. So if we just naively apply some operator to a state and measure it, then we expect the sampling cost really to be linear in the number of operators we apply. So to get down to the logarithmic dependence here, we try to sketch the time evolved state, which is really an entangled version here, using a randomized protocol called classical shadow tomography. And classical shadow consists of two key steps. The first is random quench using some quantum gate drawn from an ensemble. And second is just the measurement of qubits. After repetitive measurements, we get a classical shadow data set, which serves as the sketch of the quantum state. Let's say we want to measure capital I observables, then measuring up to some proportionality constant, measuring log I times can predict all the expectation values of the state. This log I reduction arises because we're only interested in reconstructing the state properties and not the full quantum state itself. So I won't get in the weeds too much, but we can really show that in our setup, the pre-constant in the sampling cost can be made order 1. So it's independent of the system size or locality of the O's. And once we generate these multi-observable data, we can continue with our classical post-processing step. The tool we use here is called the dynamical mode decomposition, which is an ansatz-free method. So rather than solving an ill-conditioned eigenvalue problem, here we solve a least square problem, which is numerically more stable. So the least square problem will give us a propagation matrix A that advances the observables in time increments. Essentially, the matrix A acts as time evolution in the space of observables. And by diagonalizing the matrix A, we get the eigenstate and eigenvalue information. So for illustration, we can first look at the eigenvalue estimation problem for this transverse field Ising Hamiltonian. This Hamiltonian shown at the bottom is widely studied because it models magnetic systems with competing interactions. Here we fix a time step of evolution under this Hamiltonian, and we plot the energy error on the y-axis versus the number of time steps on the x-axis. The left panel shows the result using a multi-observable signal, and the right panel shows a single observable result, as in the standard subspace or signal processing methods. So what we observe is that we see rapid energy convergence for the low-lying energies, especially for excited state where the single observable method tends to stagnate. We can also look at the performance on a chemical system where we choose this diatomic lithium hydride as our molecular benchmark. Again, we plot the energy error versus the number of time steps, and we see rapid convergence in the multi-observable setting on the left, which really gives us a substantial enhancement in accuracy only at a marginal cost. Okay, so to wrap up, we have demonstrated that time evolution can be combined with randomized techniques to perform energy calculations for many-body systems. And our ultimate goal is to explore the full potential of this framework by really extending beyond the problem of eigenvalue estimation, where I think there is quite a few interesting applications to unlock. So thank you all so much for your attention, and I also want to thank my collaborators and my advisors, Ro, Don, and Katie, for this fruitful experience at the lab. Thank you all for listening and for organizing the symposium.